In order to perform application tracing, there's two pieces of information that we're going to need. First, we're going to have to actually run our application code on the target development board, and we're going to want to include some libraries that can communicate back to SystemViewer, which is the second piece of software we need to be running. So on the target, if you take a look in our application code under the setup folder here, I mentioned earlier that we have these Segur files right here. Now the RTT is called real-time transfer, and this is the code that's going to very quickly and efficiently communicate up into our JTrace device. And then we have a couple of libraries here for SystemView, which is going to help communicate context-specific information to the software as well. Now you can see here when we originally looked at this that, hey, our entire project is 23.5K, which might seem like it's pretty big for an application that doesn't do a whole lot. But as you can see, for a production intent system, we really wouldn't include these additional files that allow us to do real-time tracing of the application code. That would be a security risk. And as you can see here, the module that communicates with SystemView is 12.1K of code space. So out of that 23.5K, almost half of it is related to just being able to transmit up our data. Now, as it turns out, RTT is actually extraordinarily fast. It can transmit data in microseconds or less. So this has very little overhead in our application code. And when we perform real-time trace, we'll actually see that in the timestamps as we look through that a lot of our application is going to be idle and that there really isn't any effect from these libraries communicating the trace data back up to our application code. Now, in order to successfully get SystemViewer to receive data, the first thing we're going to do is actually start up our application and get it in the run state. Now, at this point, it's ready to run. I also want to enable SystemViewer, so I'm going to open SystemViewer up. I'm going to go ahead and hit run here. It's going to ask me how I want to communicate to get the live streaming data. I'm going to use a USB interface. I'm communicating with an MK66, which is what's on the mPower board. This is going to be over serial wired debugging interface. We're going to let it auto detect and automatically search for the RTT and all the control blocks that are associated with it automatically in memory. So those Segur RTT blocks will create a little memory buffer in memory that's going to store the different event data that's going to get then transmitted back up to SystemViewer and allow us to see what's happening in our application code. So I'm going to go ahead and click OK. And as you can see, nothing exciting has happened yet. But what I need to do first is actually go back into my IDE that has my application code. It's sitting there waiting in main. So what I'm going to do is off screen, I'm going to go ahead and hit run. And then you're going to see the interface start filling out with information and the data for different events that are occurring inside of our system. So I'm going to let this run for a little bit. You can see, once again, real-time data. You can see the run counts changing. You can see the total run times. You can see that the event data here, the graph filled up, and also the timeline filled up. So I'm going to take a little snapshot here, and then I'm going to hit the stop button. Now at this point, I've acquired a trace of my application code. And what I want to do is go in and see if it actually behaved the way that I wanted it to. So one of the ways that I can do this is I can actually go through and I can look through the different events. And I can click on them here to see what's actually happening. You can see there's a bunch of system descriptions. And you can see here that as I start going through these different events, I move through the timeline below. So what I can do here is I can actually zoom in. I'm just going to roll here. And you can see the different events that are happening here. So you can see right here as I move in, this is going to be our system tick. So we have a system tick over here on the left-hand side. You can see there's been some calculations done for us, how many times it actually ran throughout the whole application, what its frequency is. There's an ID associated with it, and also then typical and minimum and maximum times that it required to execute. We can see here how much time the actual scheduler is taking to execute. And we can see the two tasks that we created in our application, the LED gatekeeper task and the LED controller task. And then, of course, we have an idle task that runs when there are no other tasks that need to execute and the scheduler isn't running. And you can see here the order that the tasks execute. So right here we have a system tick event occurs. Then we go into the scheduler for a little bit. We have the LED task then that executes. You can see these little blocks here actually represent additional events. So the first event here is that we enter into the actual task. We then try to get the OS, we make a call to OSQ get pointer condition. And then once we're able to do that, we continue executing. We then purge because we've executed our code. And then we leave the task and delay for the in this case, 50 milliseconds. So you can see here that each of the events that are occurring in a task, these little hash marks are actually representing them. Just by putting my cursor over, I can see how long that task took to execute in this iteration. Once a task completed, the scheduler then runs to figure out what should be the next task that executes. In this sequence, it says, oh, the LED controller task should go next. So we come in here, we can see, okay, this is the next one due. And the next event it does is it's going to put more data into that message queue that will then be received later on by the gatekeeper task when it's ready to execute again. And then another OS delay is called. The scheduler calls, and then we enter into the idle task here. And then if I scroll out a little bit, we can then see what's going on here. We can see, oh, a system tick occurs next. I can come back over here and go through this to see the different events. I can scroll through. Oh, there's a system tick. Not a whole lot occurs for a while, just a bunch of system ticks. So we enter and exit the system tick for a while. Eventually, we would get back down to where we have the next tasks start executing. So you can see right here, once again, we end up with that nice similar type of sequence. If I wanted to, I could also scroll back out, and I can visually look to see if I see any strange behavior in my code that I wouldn't expect to see. And if, for example, I saw something strange, I could then zoom in on it and try to figure out what exactly is going on. Now, the nice thing, too, is we have some additional information that we can find down here. We can see actually what the CPU load is. So this little area of the screen is showing us our CPU load for the different tasks. But if we really want to get some good context information, this context window is the best one here at the very bottom. It shows all the different activities that are occurring in our system, the system tick, the scheduler, our two LED gatekeeper and LED controller tasks, and the idle task. It actually provides us with the stack information here. We can see here that this is a higher priority than this one, so it gives us our task priority levels. And it tells us how many times that the tasks were actually executed. This can be very useful if I expect two tasks to be running at the same rate, at the same run count, but I suddenly discover that one, there's fewer counts for one task than the other. That could indicate that there's a problem or a bug in the software. Just like the same thing with the frequency. If I'm expecting the LED gatekeeper task to execute at a faster frequency than the LED controller, but just by looking at this, I can say, hey, you know what? Maybe there's something wrong with the actual code, or there's a bug somewhere. And visualizing these events in this manner makes it very easy to spot strange behaviors in our software. There's also then some very useful information from a real-time standpoint. A lot of times we just develop our code, we cross our fingers, and we hope for the best. We assume that we understand the timing of the different tasks throughout our system. It's very possible that we could end up with contentions or areas where our code is taking longer to execute than we expect it to. As we're tracing our application code, we're getting timestamps back and the events of when we enter a task, exit a task, and the events that are occurring inside that task. So that means we can get minimum runtime information. So for example, I know that the gatekeeper task, the minimum time that it executed was 0.0348 milliseconds. The maximum runtime was 0.0385. If I was expecting this to always be below 0.3 as part of a requirement, I would know that I need to go in and try to adjust that task in order to meet my real-time requirements and make sure that my system remains deterministic. The nice thing about this too then is I can also come in and look at the runtime per second, and I can start to see the actual percentage that the different tasks are executing. So you can see here that the minimum runtime, if I'm using the minimum runtime, which we typically probably wouldn't do in an analysis, we actually want to use the maximum time. But we can see that, at a minimum, we're using a 6% load of the 0.06% of the CPU for the gatekeeper task, and as much as 0.08% at the maximum runtime. So we can go through here and say, okay, you know what? We're not overtaxing our CPU. There's no reason we should run out of clock cycles, and we can design our, we know that our software isn't going to run into issues, at least related to, CPU overload, which makes this far more efficient and easy to see what's going on in our application, and we don't have to guess.